Hello, I'm Zanko from Metacraft Labs, and today I want to show you something that we're working on. This is the Codetracer time travel debugger. Here is a demo. Here you can see it, what it looks like. So Codetracer is a debugger, but which works in a way that is different from normal debuggers. Normally, you execute a program and you go through each step as it is running. With Codetracer, it works in a different way. You run the program and you record a trace. Then you can replay this trace as many times as you like. So here you see a trace of a Python script, a very simple one, which I have recorded already, and you can see how it looks. So it looks very similar to how a normal debugger would look. We can go forward like so with this button. So step in, F11. We go one step forward. So we can trace the execution of the program, okay, until we reach the end. But here we can also go back. So we can use the reverse stepping command, which is Shift F11, and we can go back one step at a time. We can also go back in other ways. I will show you later. In the trace that we have recorded, we store the execution path, and also for each step we store values. What was the state at this step? We also store the output. So here you can see the output that was produced by this script. So this is a very simple script. I want to show you next how it works to use Codetracer on a more complicated Python program, and how you can use it yourself. So as a warning, what I'm showing you right now is very new and it has a lot of bugs. But nevertheless, we believe that it can be very useful to any Python developer and who is struggling with code that they need to understand. So you're welcome to try it out and to report any issues that you find to help us make it better. All right, so let's continue with the demo. I have downloaded one popular Python package. This is the click package, which is used for building command line interfaces. And I have set it up on my laptop, and I have made a very small modification of this package so that it now has a bug. Let's check. Okay, I'm running the test suite, and as you see, something is wrong. There is a bug. A lot of the tests are failing. So now we want to debug this problem using Codetracer. To do that, we need two components. We need Codetracer itself, and we also need a separate Python package, which is called Codetracer Python Recorder. So how do you get Codetracer? At this moment, the best way to do it is to download the source code and to compile it from source. We ship releases for macOS and Linux, but the functionality that I'm going to show you right now, it's not released yet. It is available in the main repository. So that's what we're going to do right now. All right. The main repository is at GitHub. So we clone it. Our organization is called Metacraft Labs, and the repository is called Codetracer. All right, I have it already here, so this command will not work for me. Then I go in. We use Nix and drenv to set up our development environment. So you will have to install those packages yourself on your machine. Once you do that, when you enter the Codetracer folder, you type drenv allow. For me, this ran very quickly, but for you, it will download all the necessary dependencies, and which will take some time, and install them. So there's one other command that you need to run, which is git submodules update, because this repository depends on a lot of other Git repositories. Once this is done, you can build Codetracer yourself using the command just build once. All right. For me, now this will work relatively quickly because I have already built it. For you, it will take more time. Once it is done, the final binary, you can find it at src build debug bin ct. So this is the binary which you can run. All right, so here it is. Okay, that was one. I have added this binary to my pad, so I can start it from anywhere in on my machine. The other component that you need is the Codetracer Python recorder. This is a Python package that we have created, which will actually record the trace. We need this package so that we run our recorder in the same Python environment in which you're running your script. All right, so let's install it. uv pip install Codetracer Python recorder. It's installed. Okay, now here, right now, we can only record Python scripts. We're going to change that in the future, but this is the current state. And PyTest is not exactly a Python script. It's a little bit slightly different. So I have created my own very simple Python script which runs PyTest. This is the Python script test helper. This is the script that I will be running. It just runs PyTest. That's it. So if I run the script, I will run all my tests again. I can pick one failing test, this test basic, and I run it. Okay, it's failing, nothing surprising. Now I'm going to record the trace of this execution. And the way I do it is, so I replace my Python command with ct record. All right. Now I am running the script and I am recording the trace. As you can see, it takes a lot of time to actually record the trace. And this is because of several things. Here you can also see that it takes a lot of memory to record it. Well, one thing is that our recorder is not very optimized. and we are working on that, and it will be improved in future. Another issue is that right now, when we step through the execution of the script, at each step we record the values of all local and global variables, and we do it again and again and again at every step, and this takes a lot of time and resources. So it takes a lot of time to create a trace, and the trace is rather big. As I said, we will be improving that in the future, but right now we also have one feature which will allow you to avoid all of that, and this is called filtering, and I will show you this feature later in this demo. So let's see, how far are we? No, still running. It's 15 gigabytes, wow. Okay, I'm done. I'm finished. The trace is recorded, and now let's start Codetracer. All right. And here is my latest trace. All right. So it took me a lot of time to record the trace, and now it's going to take me a lot of time to open the trace. The reason is the same. The trace is very big. So you can see here, it's consuming a lot of memory. We are going to improve this feature, this issue later, but as I said, I'm going to show you later in this demo how to avoid this completely. In the meantime, let us go and examine the trace that we have recorded. So the trace is located at .local share Codetracer. Here I have a list of all the traces that I have recorded, and my last trace is trace 204. That's it. Okay, so you can see the main file which contains the trace is 5.6 gigabytes, which is obviously quite a lot. In addition to this main file, we have some metadata, and we also record all the files that have been touched during the execution of the script. So here you can go look. Let's see, home. So this is the location where my script, where a lot of the files are, and here you can see we have copied the files which we have executed. This means that this trace is completely self-contained. So you can zip it and you can send it to someone, and they can run it without needing the original repository, without needing to set up a development environment or anything else. So it makes so executing this trace is much easier than executing the original program, and it is much easier than attaching a debugger to the original program and examining what the debugger shows you. We're working on ways to make sharing of traces easier among members of a team, and in later videos I might show you what we have. All right, let's see what's going on. Well, the trace, we're still loading. Okay, so no, It takes quite a lot of time. 3 minutes already. Okay, it's done. So here is our code. You can see on the left side all the files that we have touched during the execution. And you will probably notice that there are a lot of files which we don't care about. For example, PyTest. We are running PyTest. So yeah, a lot of the code is happening in PyTest files, a lot of the execution. So here we have the terminal output. And here you can see the F, which indicates that there was a failure. So now here's the first piece of magic. Let's click on this F. When we click on it, we go to the line which generated this F. So here's this write message. Now we want to go to the failing test, and to do that we can just go back in the execution step by step until we reach the line which caused this test to fail, right? So, okay, I can go back one step at a time and so on. Actually, there are a lot of steps, so that is not very convenient. Another way to go back is using reverse step out. So what this does is we go to the caller of the current function. So now I am in this function pytest run test log report. If I click reverse step out, I go to the line which called this function. So here this function was called. I can go back another line to another reverse step out and go back again, and so on, until I finally manage to go to my tests. But as you can see here, a lot of the code that I have to go through is code that I really don't care about at all. So this is PyTest packages and other packages related to that. So we will stop tracing this right now, and we will add a filter. The filter is a file which tells us which files and which functions to trace and which files not to trace. We have a built-in filter which filters out any packages which belong to the Python standard library. This is a good default. It can be overridden if necessary, but most probably if you're tracing your own program, you really don't care what is happening in the Python standard library. So this is just unnecessary noise for you. All right, so let's look at our filters, what we can do with filtering. So to add a filter, you need to create a folder .codetracer, and in this folder you need to add a file called tracefilter.toml. I have already created one file, but it's right now turned off, so in order to turn it on, I just rename it. All right, let's see what we have inside. So here is our filter. Let's go line by line. So this is the first important line. The default command for what we do. So by default, we are going to trace every line. This is what this means. And also the default action for collecting values of different variables. By default, we are going to collect the values. We're collecting 4 types of values: values of local variables, global variables, function arguments, and return values. Then let's go forward. So this is one scope rule. So for the package called click and all sub packages, we have default action again trace, but we have we add a special filter for the value. So here we say don't record global values of global variables for any package in click or any sub package. This is a good choice because a large number of the global variables are things that we don't really care about. So those are packages, function definitions, class definitions, some built-in variables that Python has. And those are things that very often we don't care about. Sometimes we use global variables to have state. And in those cases, you can add a special filter which tells us, okay, those specific variables that I want them to be recorded. But yeah, in general, it's a good choice to by default drop the global variables. Here I have another rule like this. So for the package called all packages which start with the prefix test, again I'm going to drop all global variables. Then here I have three rules which tell me to skip tracing for packages which start with pytest, with underscore pytest, and with pluggy. So those three modules, they belong to pytest, and they contain a lot of logic that we go through every time, but we don't care about at all. We assume that pytest does not contain our bug. It must be in our own package, so we will not trace any of those packages. All right, so this is my filter. As you can see, it's something relatively common sense. And one other thing that you can see is that this filter is not really specific to my case right now, that I'm looking for a bug in a specific file. So once I have this filter in my project, most probably I will not need to modify it for most of the traces that I create. All right. So we have this filter. Let's record the trace again. All right. Last time it took about 70 seconds. Now it was 2 seconds. Now that's much better. Let's start it. Here is my trace. It still takes some time. Last time it took around 3 minutes. Now it's much faster. Let's see my trace right now. How big is it? I think this is trace 205. All right, so last time it was 5 gigabytes, now it's 158 megabytes. That's much better, and it is good enough. If we really want, we can limit more, probably, but yeah, that is good enough to work with. All right, now let's find our bug. We click here again. This time, actually, the line which generated this F symbol is not in our trace because we filtered it out, but okay, so we don't really see what exactly caused that. It was somewhere here. But let's go one step back. When we go one step back, we're going to go to the last line which was recorded. in our trace before this f appeared. So reverse step in. Okay, and here is the offending assert. So this assert caused our error. You can see that there is this value variable called. It's a local variable, and it has values. So here you can see the values, and you can see the values in the state here also. The values are eager3, eager1, eager2, and then normal1, normal3, normal2, and missing at the end. But it is supposed to be equal eager2, eager1, eager3, and then normal2, normal3, normal1, and missing at the end. So because those two values are different, this assert fails. Now we want to find out why this is happening. So this code variable, as you can see it here, here it is created, and you can see that here this memo function adds values to it. Then we can see this memo function is being called here. All right. So the first value is eager3, but it is supposed to be eager2. Let's go to the beginning. So I can jump to this line. And so here I'm at the beginning of the test. And here this is empty. Then let's jump to this line. So this is the first time we actually append a value, and the value that we append is eager3. But it was supposed to be eager2, right? So there is an error. So now we have to go back the call stack and see what caused this value to happen. I'm going to use the reverse step out. So this will go to the caller of this memo function. What called it? So here this function was called. And you see the value is eager3, but it is supposed to be eager2. Let's see what created this value eager3. Again, we go back. Here, this function was so this is the function that we're executing right now, process value, and you can see that the self argument, again, it's eager flag 3, so it's the same. Obviously, this function was called with the wrong arguments. Let's continue tracing back. We're going to use reverse step out to see what called this function. Okay, here. Okay, then this function was called by this process value. Again, the self argument is wrong, so we go back. All right, so then we have this thing, handle parse result, which returns eager3. And here I see everywhere eager3, and myself, the self value is again eager3. So obviously this function was called with the wrong arguments. So let's go back. All right, we're here. There is an iterator which emits params, and the first value that is emitted by this iterator is this eager3. So apparently it shouldn't be happening. So the first should be eager2, not eager flag 3. So obviously this iterator is emitting the wrong values. By the way, here you can see that we can just time travel to the other values that were emitted by this iterator. So we can just, this is nice functionality that you can play with for any loops that you see, any for loops. You can go examine all iterations. But okay, so here The problem is obviously in this iterator. All right. Let's go one step back and let's go into this iterator to see what's happening. Step in, so reverse step in. All right, so here, this is the iterator, iter params for processing. And we can look at it. So, what does it do? So it has those invocation order, and there is this declaration order, which is not shown for some reason. And there is a sort function, and we just sort this declaration order array with the sort function. That's what we do, right? Now we can play with the sort function, so we can now go and see. Now we are this is the last time we call the sort function. We're inside it. Let's see. Let's go back like this. Yeah. So we're calling the sort function with item option help, right? Okay, then we're calling it with item normal flag 3. Okay, so let's see item normal flag 2. And we have index. So for normal flag 2, the index is -2. So the index is opposite of this, the index of the invocation order. So the invocation order is a sequence, and we're sorting declaration order with the opposite, in the opposite order from what we have sorted, the invocation order. Okay, so that's what we see. So is this the, let's go back and see what is happening in our test. Okay, so this is the test. So let's see, what is the declaration order? So first we have declared missing, then eager flag 1, flag 2, flag 3, normal flag 1, normal flag 2, normal flag 3. What is the invocation order? It is eager flag 2, then flag 1. And I suspect that the eager arguments have to be processed before the normal argument. So then we have normal flag 2, then eager flag 3. So here, this is the invocation order. You can see it here. And what do we expect? So we expect that the first argument is eager 2, then eager 1, then eager 3, which is equal to this invocation order. Eager flag 2, eager 1, and then eager 3. But what do we get? So we get eager 3, eager 1, eager 2. So it is, the order is opposite of the invocation order, right? So the order is eager 3, eager 1, eager 2. It is opposite of the invocation order. Why is it opposite? Because we just saw, right? Because this is what we are doing. We are, so here we're sorting this array in the opposite order of the invocation order. And in the test, we expect that it is sorted in the invocation order, not in the opposite. So maybe the problem is that maybe this is, the sort order is the problem, right? That's a reasonable assumption to make. So let's check, is this correct? Now I will edit the offending line. Here is the line. So we remove this, and now the sort order of this array is the same as the invocation order. Let's run my tests suite. All right. Now all tests pass. So we found our bug and we're happy. Obviously, I put this bug, right? But I'm not familiar with this Click project. So when I was preparing for this demo, I set up the project to be able to run it myself on the laptop. Then I opened a random file, more or less, a random location, and then made this very small change. And then I ran the test. I saw that they're failing, and so that was it. I don't know its internal logic. I don't understand the code at all. Then when I traced this failing test, I went through the execution that was happening, and what happened. So I could very easily go to the place which was the origin of the bug, and this is not related to the fact that I created it. It is just a relatively simple process to do this. And also I managed to understand one part of the logic of this package, one small part of the code, and I understood how it works. And how did I understand it? I just traced the execution. So at the end of this exercise, I know a little bit of the internal workings of the Click package, and I managed to fix a bug very easily in a repository in some code base which is unfamiliar to me. So this is the value that we can that Codetracer can give you. We as programmers, we write code, and the purpose of the code is to be executed. So we write code which is executed step by step in a deterministic way on a computer. But when we try to understand the code, we don't use this fact that the code is supposed to be executed to actually understand it. Usually, what do we do? For example, when I have to understand a PR that some other developer made, I open the PR in GitHub and I just read it. I don't execute it. Maybe, or at least I don't execute it on a machine. I try to build a mental model of the code by just reading it, and maybe I try to execute it in my mind. This is a very mentally challenging process, and it is completely unnecessary, because at the end of the day the code is supposed to be executed. It's just that we don't really have very good tooling to help us execute the code line by line, so that we can see how the execution is happening and so that we can understand it better. For one reason or another, our tooling is lacking in this area. So if I have a bug, what do we do usually? The most popular way of looking for bugs is using print statements. So I basically treat my code like a black box. I don't know what's going on inside, and I just run it. I see the output, and based on this output, I try to reconstruct in my mind how the execution went. Again, this is frustrating and mentally challenging way of understanding a piece of code. So the code is supposed to be executed. So the easiest way to understand it is to actually execute it and to observe this execution. We have debuggers. Debuggers nowadays don't seem to be very popular. They are popular for some languages, but not for others. So for example, C++ developers, they might use debuggers a little bit more. Python developers probably a little bit less. Debuggers can be helpful, but they have their issues as well. If you want to understand how a piece of code works with a debugger, you will have to restart it more than the process more than once, because you go to a point and then you understand, oh, what I care about was before this point, so I have to restart the process again and then go back to this previous line, and I have to repeat this process several times until I can pinpoint the line or the lines that I care about. Another issue with debuggers is that it is actually quite difficult to set up in some cases, so that they're not very easy. Another issue is that, well, if I'm a code reviewer, I need to set up the environment that the developer had on their machine. I have to set up on my machine so that I can run their code, and then I can set up the debugger so that I can use the debugger to understand the code that the developer gave me to review. So all of this is very complicated. With Codetracer, we can make this whole process of understanding code much easier, and I show you how. So you're welcome to now try it out yourself. You can go to codetracer.com, you can go to our GitHub repository, you can download the packages and see how it works for you, and to tell us what you think. We welcome any advice how to improve this product, any issues, any bug fixes, and any other comments. So, thank you. I hope this thing that we have created can make your life a little bit easier from now on. Bye-bye.